Okay, so here I want to find I want to use Newton's method to find the value where ln of x equals 6.
ln.
In Mathematica, ln is log.
Okay, just that.
So I want to find where ln x equals 6. So how can I use Newton's method to do that?
Well, so I guess what I can do is I'm going to make a couple more things to modify this function.
Well,
Well,
you should be able to do it with the program you have. I don't want you to have to make modifications.
well, I can make a new function that's this function ln x minus ln 6. So that function is going to be 0 or have a root.
Not where it equals ln 6.
Or,
where I want to know where ln x equals 6.
okay, so we can have a function ln x minus 6 equals 0, and that'll have a root at the correct x value.
Okay, so what function are we going to use?
So we just use ln x minus 6.
Okay, now you know the exact value of this. Where does ln x equal 6?
It would equal 6 at e to the 6th.
Okay, but you don't know, I assume, what e to the 6th is. So we're pretending we don't have a computer to calculate e to the 6th.
Well,
so what would we use as our first estimate?
Well, I mean, we're not gonna have to worry about it doesn't have a lot of waves, so we can guess semi far away, and we should still be able to reach the root eventually. So we can guess 2 to the 6th. So I'll guess 64.
Okay.
Is our initial guess, and we can do 5 runs at first. We might need more.
All right.
Okay. That seems to have got it pretty close.
Yeah, although we're not even sure with 5 runs if we're at even 1 decimal point of accuracy. Yeah, we probably are.
Let's do 10 runs. Okay. So it looks like
Scroll that all the way down to the pi over 2 cents. A little bit other way.
so we have it's about 403.42879.
Yeah, and we can see that this isn't changing.
So we got it.
Okay, so now we can check if your program has
So the n of e to the 6th.
exp 6.
exp.
Capital exp.
Okay. Yeah, so we got it.
And check it to 20.
That's just comma 20. 793492735 1 2 2. So we got it 2.
Yeah.
Yeah.
That's pretty cool. All right. Well, hey, good job. So this shows you how to write a nice little simple, straightforward program for Newton's method, and how to use it not just to find roots of equations, but actually to find where functions are equal to specific values. You just change the function by subtracting that value away, and then you see what happens. We haven't gone into the details of when Newton's method works or when it fails, but this is a good starting point for Newton's method. It's very important, and we can see that even here we could use it to calculate e to the 6th to 20 decimal places after 1, 2, 3, 4, 5, 6, 7 iterations, even with a initial guess that was just not all that good.
I mean, it's like almost 300 off.
Yeah, so if we knew it was around 400, say, somehow we knew that.
So we get it after
we get
4.
Yeah, after 4 iterations we get 20 decimal points of accuracy. And you can imagine if you needed to do 4 iterations by hand, you probably could do that. So this would be a way, if you were in Newton's time, where you could calculate things to a lot of accuracy. All right, good job.